Hi listeners, Benjamin here. This week marks the 10th anniversary of a momentous moment in science, the detection of gravitational waves. This detection was the climax of a cosmic dance between two black holes. After spending an eternity spiraling closer and closer to each other, eventually these black holes merged. A cataclysmic event that sent ripples in space-time across the universe that were detected by the LIGO facilities in the US. This detection was the culmination of a story that began over 100 years ago when a certain Albert Einstein predicted that gravitational waves might exist. Back in 2019, I spoke to Cole Miller from the University of Maryland in the US, who'd co-written a review in Nature about the discovery of gravitational waves. To mark the anniversary, we're rebroadcasting an edited version of this podcast, which began with Cole explaining how the story got off to a bit of a bumpy start.
Einstein came up with the final version of his general theory of relativity in 1915. And just the next year, he came up with the thought about whether there could be waves related to gravity. Remarkably, though, Einstein made some significant mathematical errors in that first paper, and even a corrected version in 1918 had errors, and he had conceptual problems with it one way or the other. He published papers saying that gravitational waves don't exist, and he published papers saying they do exist. So it was really only in the 1950s where people really accepted that gravitational waves were real things. But detecting them was another story.
According to Einstein's general theory of relativity, each time two objects orbit each other, the system loses a fraction of its energy, which radiates out as gravitational waves. Removing energy like this brings the objects a tiny bit closer together and makes their orbit a tiny bit faster. As gravitational waves only deform space-time a tiny amount, they're difficult to directly detect. The first indication of their existence actually came indirectly, via the discovery of a pair of orbiting neutron stars. This binary system was identified back in 1974. One of the stars in the pair is a pulsar, a type of neutron star that fires out flashes of electromagnetic radiation with clockwork precision.
Pulsars are such extraordinarily good clocks that it's possible to measure an orbital shrinkage on the order of a millimeter per day. And with that type of precision, even though it will take hundreds of millions or sometimes billions of years for these systems to finally coalesce and merge, it is possible to see the gradual reduction in the orbit by careful pulsar timing over years to decades.
Accurate measurements of the two orbits of the stars show that they are slowly getting closer together, which is exactly what you would expect if gravitational waves exist. But this was an indirect detection. Getting a direct detection of gravitational waves was a whole different ballgame for physicists. To detect the subtle presence of these waves required a detector of exquisite precision.
Nonetheless, people starting with Joseph Weber, who was a professor at the University of Maryland, and carrying on with a number of people, notably Rainer Weiss at MIT, began to think about the prospects. And the method that ultimately became successful used lasers.
The observatory that picked up gravitational waves as they washed over the Earth was the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, which is based in the US and is part of a global network of interferometers that includes the Virgo facility in Italy and the soon-to-be operational Kagura detector in Japan. Now, LIGO is actually a pair of detectors. Each detector is an L shape, with a pair of arms 4 kilometers long. A laser is fired into the L and split into two. The split beam travels down to the ends of the arms before bouncing back off mirrors to where they originated. Normally, the time it takes for the two laser beams to reach the ends of the arms and back is exactly the same. So they strike and cancel each other out. But when gravitational waves pass through LIGO, they stretch space-time, which makes tiny alterations to the lengths of the arms. This changes the timing of the laser beams, which then no longer cancel each other out, producing a signal that can be detected. LIGO, one of the US National Science Foundation's most expensive projects, began searching for gravitational waves when it first opened in 2002. But it wasn't until the observatory had had some upgrades to make it more sensitive that researchers struck gold.
On September 14th, 2015, a signal was discovered which lasted only a couple tenths of a second. And this signal showed clear oscillation in space-time seen by the two LIGO detectors, one in Hanford, Washington, the other in Livingston, Louisiana, which are about 3,000 kilometers apart. And this looked absolutely like what people expected to find if two black holes were to spiral together.
The event, with the catchy title of GW150914, captured the last spirals of these two black holes as they orbited closer and closer, whirling around each other many times a second, releasing more gravitational waves until they smashed together, sending a blast of waves across the universe. Sometimes in science, the stars, or maybe in this case I suppose, the black holes align, and luck is on your side. LIGO technically wasn't in full research mode. That was due to commence a few days later, but crucially, it was ready.
The chances of seeing something as strong as was seen were not good. The community got extremely lucky to see it this well. It's almost as if the universe was waiting to show off when the LIGO detectors were ready.
And what do two colliding black holes sound like? Here's the signal that LIGO detected, converted into frequencies that are easier for us to hear. And here it is once more, just in case you missed it. Well, all right, that might be a bit underwhelming in audio form, but this was an enormous moment for science. Rainer Weiss, Barry Barish, and Kip Thorne shared the 2017 Nobel Prize for Physics for their work on the detection of gravitational waves. At the ceremony, Weiss gave credit to the hundreds of other scientists from institutions around the globe whose work allowed the detection to happen. And the discovery has given researchers an insight into the general theory of relativity put forward by Albert Einstein over 100 years ago.
It's important to remember that, of course, general relativity, Einstein's theory of gravity, has passed every test that it's been put to. However, in distinction to our theories of other fundamental forces, gravity is very difficult to test. It may not seem obvious to you if you happen to trip and fall, but gravity, as we experience it, is really, really weak. When you're thinking about the type of gravity that would be involved in black holes or their lesser-known cousins, neutron stars, these are so strong that it is entirely possible that the true nature of gravity is different from what Einstein suggested, but that the differences only show up that gravity is very strong. Observing gravitational waves from black holes merging gives us direct access to this strong gravity nature. And Einstein is still doing very well, by the way.
Being able to detect gravitational waves gives physicists a new way to probe the universe. But the LIGO detection was just the first step. To date, several more black hole mergers have been catalogued, as well as collisions between neutron stars. Cole thinks that our ability to detect gravitational waves will help researchers to answer many questions about the universe.
We expect to learn tremendous things about physics. We're going to have many more of these events. We'll learn more about gravity. We'll learn more about neutron star mergers. What are neutron stars made of? What is in their centers? These are puzzles that have to be resolved by astronomical observations. And it's something that is going to be going on at an accelerated pace as the sensitivity of detectors increases, but also as other types of detectors come up.
In addition to upgrades to current detectors, new ones are being designed and built. But not just here on Earth. In the 2030s, researchers are looking to space with the Laser Interferometer Space Antenna, or LISA, mission. LISA will send up a trio of probes that will sit millions of kilometers away from each other and usher in an era of even more sensitive detection. Quite what these new detectors will discover remains to be seen, and it's important to remember that researchers have only been surfing the gravitational waves for a few years. Nevertheless, September the 14th, 2015 will go down in history as the date that these waves were first directly detected.